Good evening, everyone. I'm thrilled to welcome Dr. Robert Jackler this evening from the Stanford University School of Medicine, where he leads the Stanford Initiative to Cure Hearing Loss, which has a mission to create biological cures for inner ear hearing loss through research. And also want to welcome CART provider Diana Nichols. Diana is from Alternative Communication Services, ACS. Thank you very much, Diana, for providing CART this evening. I know Dr. Jackler has a lot of information to go through, so I'll let you go ahead and get started. Thank you so much for presenting tonight.
Well, thank you very much, Nancy, and I will do the best I can to speak clearly and distinctly. And I'm very grateful for the captioner for helping to supplement the words that I say. And I realize that we have a variety of individuals with different levels of expertise and knowledge about hearing. So I'm going to provide some overviews about hearing loss in the context that we're talking about when we talk about our initiative to cure hearing loss here at Stanford and elsewhere. Now, about 10 years ago, we began to put together a group of scientists from around the world, literally, with the goal of overcoming sensory hearing loss. That is to say, the vast majority of hearing loss is not nerve hearing loss, as is often said. That's erroneous. The vast majority of it comes from the hair cells within the cochlea in the inner ear. And although we have the ability to treat many ear problems, our ability to treat problems of the cochlea is rudimentary as of 2014. But we live in a time and a place when I believe that's going to change. And there's great hope that it will be changing based on biological advances that is going on in the research labs around the world. And that there is hope that this comes in time. Now, most of you realize that hearing loss is an enormous problem around the world. 2 to 3 of every children born in America are born deaf. Half of seniors, including me, have significant hearing loss. And it is things that affect our ability to enjoy life, to communicate with friends and family, and on the job. It's estimated that there are 36 million Americans who have impaired hearing. You know, as we look at what happens with older folks, and the graying of the population, not only in America but around the developed world, is there are so many more of us living to older ages who really want to live active lifestyles and to be engaged in all sorts of activities. And you know, hearing loss really leads to isolation socially. It's hard to go to restaurants. It's difficult to enjoy live theater and music, as you all well know. I always appreciate Helen Keller had a unique perspective. She was not only deaf, but she was blind. And she says, you know, blindness separates us from things, but deafness separates us from people. When you think about what makes us human, it's the ability to communicate with our children, with our parents, with our friends, with our coworkers, and to bring us together to common purpose. Now, when we talk about the ear, really, this is not the ear most of us ear doctors talk about. In fact, problems with the external ear are largely addressed by plastic surgeons and don't have that much to do with hearing. Now, this drawing is, I think, a beautiful work of art and also has an enormous amount of accurate information. For the last 20 years, I've worked together with an artist named Christine Graylock, and she's terrific. Can you see my arrow moving across? Am I able to annotate? I think I am. Let's see. Sound comes down the ear canal. The vibrations go through 3 bones to the inner ear. The inner ear, the cochlea, sends a signal that goes up the auditory nerve to the pons, and from there up to the primary auditory cortex and along to the visual side, to the language side, etc., to help you understand what's being said. Now, just to understand, there are 3 parts of the ear: the outer ear, the middle ear, which, as you see here, is the eardrum and the 3 hearing bones, and the inner ear that has a balance side and also has a hearing side. And the term cochlea is simply Greek for snail. Now, within the 2 3/4 turns of the cochlea is the area where sound is actually understood, or at least is transmitted, and that is called the organ of Corti. And the organ of Corti is where the hair cells are that generate signals that go down the hearing nerve to the brain, as we'll see. Now, within the cochlea, the base term is high frequencies, and the apex here is low frequencies. Now, if we zero in on the organ of Corti and we look down, you will see that there are hair cells, a series of them. The outer hair cells here, those are involved in modifying the environment of the inner hair cells here. These are the primary ones that send signals up to the brain. And the role of the outer hair cells is to modify the environment of the inner hair cells and help to tune the inner ear. Now, here's an enlarged picture of the organ of Corti, and this is the area that we're most interested in when we talk about regenerating lost hearing. More about this soon. Now, this graphic doesn't play. I have a number of videos, and I apologize, the technology of this online webinar does not allow. But if you hit a tuning fork with a low frequency, there will be a primary bump here. If you hit a tuning fork with a high frequency, other way, low frequency here, high frequency here. Imagine that this is like a jump rope tied to the wall, and when you move up and down with your arm, it forms a standing wave, and that's the location where those hair cells are primarily stimulated. Now, after the hair cells, here are the hair cell row spiraling up through the cochlea. Each domain, each place is a key on the piano keyboard. You have the spiral ganglion that are the first nerve fibers, and then every fiber shoots on towards the brain. Now, once the hearing leaves the cochlea, it goes up through the brainstem, crosses over, and then comes on up into the floor of the insula, the temporal lobe, and then has many radiations and communications to language and memory and cognition. Now, I'm going to share with you, with apologies to Charles Dickens, a tale of two ears. That is to say, the middle ear and the inner ear. And in Dickens' time, nothing could be done about problems of the eardrum and hearing bones. But over the 20th century, we have conquered largely problems with the eardrum and the hearing bones, both through medication and through the ability to replace them when they're harmed by disease or lost. But today, we are really very little further along in the inner ear than we were in Charles Dickens' time. But that, we hope, is about to change in the coming years. So these are some pictures of holes in the eardrum, a little one, a larger one, and then one entirely filling the ear. Here you see the first hearing bone, the second one called the incus, and here's the stapes bone down there. Now, this problem might look very daunting, but in fact, it is repairable in the high 90% today. And to give you an idea how this is done, this is one of Chris Graylap's drawings with my art, and here you see the hole, and what we're doing is we're moving the ear canal skin inward, turning the eardrum over, and then we slide in the patient's own tissue, fold back the eardrum and the ear canal skin, and then here is the repair. And that will have new blood vessels grow in it and generally restore hearing very nicely and also prevent infection. Now, some of you may have a disease called otosclerosis. And in otosclerosis, there is a calcium plaque that forms right here. And that stapes bone, if you see me in the window, the eardrum vibrates, and the stapes, through the linkage, pumps the hearing into the inner ear like a piston. And when that has become frozen, it's possible to take a little wire and replace it. Now, I don't recommend you do your own surgery at home, but I'm going to give you a little idea about what modern ear microsurgery is like. So here's the ear canal, the eardrum, the incus, the second bone of hearing, the stapes. This is the inner ear down here with the utricle and the sacral. And here we've turned the eardrum forward, and you can see we're measuring here from the incus to the footplate of the stapes. We then cut across the joint to separate it. We then make sure that these outer bones actually still move. We cut a little tendon. We then remove the upper part of the stapes bone and we take it away. And then in the bottom of the stapes, we make a tiny hole. Now, to give you an idea, the real size of this hole is kind of like that little spot over here. It is 0.7 millimeters. It's very tiny and very delicate to open this up. We then put in the device, which is a piston. The size of this is the size of a comma on a piece of paper. Very tiny. Then it's crimped onto the incus with a clever little device called a gripper. And then here it is in position, and there it's done. Now, this operation here, when it's finished, has a rate of improving hearing of about 90%. Really quite successful. It's been thought that Beethoven had otosclerosis, and if he were around today, he would not have been deaf when he wrote the Ninth Symphony, which I've always found extraordinary that he was able to do that. Now, if other hearing bones are lost, you see in this image, we've lost the malleus and we've lost the incus. We use a piece of titanium to reconnect. And this is affectionately known as a PORP, P-O-R-P. I'm not great at spelling with a mouse. Partial ossicle replacement prosthesis. It's a piece of titanium and it grips on, and again, with modern technology, this works very well in replacing lost hearing bones. Now, in the Stanford Initiative to Cure Hearing Loss, we're really looking at hearing loss not only in older people, but also children born deaf, those in the military who sadly may have been exposed to IEDs in Afghanistan, those who have been rock musicians and listen to amplified music every day. Now here is a normal hearing portion of the inner ear with its hair cells intact. Here's what happens in hearing loss. Notice that we still have the nerve fibers here. Years ago, it used to be thought the nerve wasn't there. So this is the substrate right here, that membrane of cells that we need to work on to bring them back to having an organ of courting. This video doesn't run, but it shows the hair cells going away as hearing loss occurs. Now, let's talk for a moment about hearing. And you can see here, this is an audiogram. Many of you may have seen these. This is like a piano keyboard. The low notes, oh, I have to change color. Let's see here. I wonder if it lets me. Nope. Okay, so the lower notes to the left, the higher notes to the right. Normal hearing is around through 20 decibels. This is total deafness, way down at the bottom. The reason you have a little response at the low frequencies is you can feel them, and you have a non-auditory percept. Now, the most important thing we listen to is people talking. And you can see that is about 500 to 3,000 hertz, the so-called speech box. Now, there are different parts of speech. Vowels are in the low tones. Ah, E, oo, O. In the high frequencies are the consonant sounds. And the consonant sounds over here are the most important ones for conveying speech to most of us with a partial hearing loss. Like P, K, F, D. Those run together when you have a high frequency hearing loss. Now, with aging, which is the most common form of partial hearing loss, you start to see the hearing go down in the high frequencies, further and further down over time. Notice that this is starting to affect the high frequencies here. And that's beginning to be when people have difficulty in noisy environments. Now, many of you may have heard about the cochlear implant. Now, this is truly a miraculous device. It is the first time that a human sense that has been lost has actually been restored. There are about 300,000 to 400,000 people around the world who now use cochlear implant devices. And many of you, perhaps, who are here with us tonight are. And the idea of the cochlear implant is that it coils around within the cochlea, within the scala. And these electrodes send out electric current. And when they do it, they activate a particular domain of the hearing nerve, and that particular domain represents different frequencies. Now, just for those of you who have a voyeuristic interest in surgery, this is how a device is inserted and coils around within the cochlea. It doesn't go all the way to the top. It goes much lower than that, about 1.5 turns, for several reasons, partly because the nerves cascade down from above to a lower level. Now, this animation doesn't work, but the different electrodes stimulate different populations of the hearing nerve. Now, a child born deaf today who has a cochlear implant doesn't necessarily need to go to a special school for hard of hearing kids. They may learn sign language, but when they're communicating, they're going to communicate dominantly orally in a hearing world. And this is a very major change. We have a number of students here at Stanford who participated in mainstream education and are now brilliant and doing great, even though they were born completely without hearing. Now, I don't mean to say that cochlear implants are going to be the panacea for hearing loss. They don't replace natural hearing. They are far better than total deafness, as many of you know, but they are not normal hearing, and they require all of this technology and devices. Now, the Stanford Initiative to Cure Hearing Loss, we like to think of it as our Manhattan Project. It's a large-scale, multidisciplinary, because great discoveries come at the intersection of different fields. It involves molecular biologists, geneticists, engineers, computer scientists, many different people, developmental biologists coming together. And our goal is to go into clinical trials with an effective cure for at least some deafness within a decade or so. Don't ask me, please, to commit it's a decade. I don't know, frankly. It depends a lot upon the resources brought in and how scientifically successful we are. And we'll talk more about this. Now, this whole field began with the realization that unlike humans, when you lose a hair cell as a human, it's gone and gone forever. And you have a mere few 10,000 hair cells. That's a tiny number of these specialized cells. What was found by Ed Rubel and others in the University of Washington is that in birds and amphibians, when you lose the hair cells, they grow them back. And that was, you might think how spectacular, but think about it. When you cut yourself, you heal. When you break a bone, you heal. It isn't unprecedented for the human body to repair itself, but the inner ear in humans currently lacks this kind of reparative ability. Now, if you think about the issue about regeneration, we've had stem cell therapies for some years to replace the bone marrow in people who've had chemotherapy and leukemia, for example. But solid organs have a special problem, and that is architecture. So if you've lost your liver, as seen here, all you have is a scarred little lump with none of the collecting ducts, with none of the blood vessels, and with none of the structure. But if you're deaf, you still have the elegant cochlear spiral. You still have the scala tympani and the scala vestibuli, and the scala media. You still have the auditory nerves. Cochlear implants have taught us how well the auditory nerves survive. So this tells us that the necessity of what has to be replaced for the inner ear is relatively modest compared with other solid tumors. Now, many of you have heard about stem cells, but treatment with cells is but one strategy for restoring the lost inner ear. We tend to call it cellular therapy, where cells are passed over. There's also genetic reprogramming, but also, and very likely, the most promising will be molecular modulation, putting in small molecules, if you will, drugs, that trick the inner ear into doing what it did inside your mother when you were developing. So I like to think of a stem cell as a spherical cell which, injected in a laboratory animal, produces a scientific paper. Scientists amongst you will understand this. Now, when we talk about cells, early on, people talked about embryos and talked about cord blood. But the revolution that has happened in recent years is what's called induced pluripotential cells. So imagine someone took a little piece of your skin or a little bit of fat. No, we're not advocating liposuction. But these cells can then be taken back to a more primitive state and then brought forward through a series of clever molecular steps to become a hair cell. In what you might think to be a Hail Mary, there is some sign that we can take differentiated cells like skin and go directly over to a hair cell without going through a primitive cell on the way. Again, induced pluripotential cells. The Nobel Prize was on this about 2 years ago. The concept in cellular therapy is to take that scarred membrane and implant cells and then restore hair cell membrane. Now, if you were born deaf, you have a genetic defect within your hair cells. So every one, these are scar cells, but every cell in the nucleus has a flaw. And the DNA has an error in it somewhere that says, oh, it can't make the hearing apparatus correct. So you can't just take, like, say, a child's skin cell, transform it into hair cells and implant it, because those hair cells will have that same deficiency. That's where you need to look at gene therapy. And this is shown as a virus particle carrying a fragment of DNA, which has, if you will, the corrective code. And there's much research going on splicing DNA into these cells, both to turn them on to become hair cells, but also to become happy and functioning hair cells. Also, the use of molecules. Now, it turns out that there are known signaling pathways that will take one of these scar cells and turn it into a hair cell. And today, we can take a robotic system with 100,000 wells, with many, many small molecules we know are bioactive, and try to pick out that small chemical that will actually switch on that process. Now, so there are two ways of thinking about this. One is transdifferentiating one of the scar cells into a hair cell. The problem with that is you'd eventually deplete all the cells. Proliferation, where you actually proliferate it so there's a daughter cell and then convert it into a hair cell and its supporting cell, is more likely the pathway forward. This video doesn't run here. Now, this is a very important concept. Every one of us has been able to form a healthy inner ear when we were babies inside our moms. So inside our genes, inside those nucleuses, is a perfect command structure for forming an inner ear. Now, you might realize that development, to go from this simple phase to the beginnings of an organ of Corti to a mature organ of Corti, is a very complicated process, and that is true. But it turns out that there are master genes, master developmental regulatory genes. And I think I have a slide here. No, let's go back. So imagine and you're going to hear more and more about a gene called ATO1. For you scientists, that's atonal homolog 1. Now, what happens is, if you think about development, there are all these stages, one point to another point to another point, and different substances control that development at each point, and a whole cascade of events have to happen. But imagine that here you have a master regulatory gene, ATO1. If you turn on that gene, there's a self-organizing cascade of events beyond it that leads to the formation of hair cells. So people are looking at switching on that gene and allowing it to do, through its program, to create new organ of cording. And in animals, this can be done today. Now, we know in our initiative that there are a number of different ways that we might overcome this. Cellular therapy with stem cells, gene therapy, molecular therapy, even advanced neural stimulation. We have groups working on all of these areas. And our goal is a bit like a horse race. You know, we have a bunch of different ways going. When one gets ahead, we're going to move all of our resources over to the one that looks like it's getting to the goal line first. Right now, these three are heaviest in our area. Now, we have a great group of faculty at Stanford. We have about 100 people. I'm going to briefly introduce you to some of these individuals in that way. This is our research group. If I showed you our doctors, they're all in white shirts and ties. When you look at the research group, it's straight out of Hawaiian shirts, right? They're very casual. They feel that if you wear a tie, you have 20 points of IQ less. Stefan Heller, famously, in 2003, first identified stem cells in the inner ear that could be converted into hair cells. Stefan Heller was recruited from Harvard to Stanford the year after, and we have built together, we sought to go out and hire the best and brightest people. And we're not done with that. We're still doing that. But we've assembled an incredible all-star group of people. It isn't every day when you recruit someone that it's in the Sunday New York Times. We all got a kick out of this. But Stefan has been just a wonderful leader in that. And, you know, his work is to create not only in animals, but increasingly anticipating work in humans. He is indefatigable. He is a force of nature, sort of like Winston Churchill. He is determined to eventually overcome hearing loss. And this is Stefan's lab. This is one of the different labs. Tony Ritchie is probably the world's best auditory physiologist. Now, Tony works on a rig like this where you will have a hair cell membrane with all sorts of recordings that go over to some fancy electronics. The reason that's important, you may produce a cell that looks like a hair cell, but unless it functions like a hair cell, it isn't. And so Tony is able to actually measure these and to show what these cells work characteristically. Alan Chang is both a pediatric ear doctor, a surgeon, but also a brilliant researcher. And what Alan has been able to do, he has been able to work developmentally and find where the different cells that create the regenerated hair cells came from. So he's able to identify exactly the cell population so that we can work specifically in a targeted way. John Ogilvie is an engineer and a surgeon, and he brings in many engineering skills. So he does things like optical coherence tomography, which is a very fancy pathway that leads us to begin to identify within the inner ear how the hair cells work when they're regenerated. He also works in infrared spectroscopy. This device on her head, when you stimulate the ear, either with the cochlear implant or sound, will show the different parts of the brain that are activated. So imagine you have a deaf 2-year-old who can't really tell you what they hear and what they don't hear. He's now working to be able to bypass the need for the child to say, that sounds better, or this sounds better, and actually in a non-invasive way, by looking at blood flow in the brain through infrared spectroscopy, to be able to design the optimal programming for cochlear implants. This is my colleague Nicholas Blevins. Nick is also an engineer, but he's also a computer simulator. And he works on microendoscopy. So this is actually a little endoscope right here. It's 1 millimeter or less. It can peer at the living organ of Cordy in animals while we drip in cells or whether we drip in molecules. So this is it's never been done before, but as you can imagine someday, when it comes to placing cells in the inner ear, you can't just slop them in and hope they go the right place. If they implant here or here or here, it's not going to work. You have to have a specific architecture. You have to rebuild the ear. One thought we have, you may have heard of 3D printers. Well, 3D printers lay one layer after another layer after another layer. Imagine a printer that printed living human cells. In fact, your cells that were genetically manipulated to form nerves and supporting cells and hair cells. And you lay them down, and with that printer, you create an organ of Cordy from your own cells, and then you lay that in to the place that it's necessary. Kay Chang, we have a whole group working on drugs that hurt the ear. And this is actually an interesting story. It's partly Kay's work, but also others, Tony Ritchie and Alan Chang. And it gives a good example of how intersections between fields work. Now, many of you may know that there are drugs called aminoglycosides. They usually end with mycin, streptomycin, gentamicin, that will destroy the inner ears in many people. What Tony Ritchie had the notion that if you design an aminoglycoside that won't fit through, so in every cell wall there's a pore, and it turns out that we've been able to study the molecule and the pore and figure out why the drug gets into the hair cells. By sticking something out on the side of it so that it can't go through the pore, but that it still kills the bacteria, you can actually design it. So working with chemical engineering, we actually gave them the structural biology. We suggested add these groups here, and in fact, it doesn't harm hearing, and it works well against the bacteria. So this is a really brilliant collaboration. It's not yet ready for humans because, as you know, drugs take many years to come out, but it's that kind of drug design from basic principle, from understanding the structure and the biology and saying this is what we want to do, and then actually producing it is a wonderful paradigm. Mirna Mustafa is an auditory geneticist, and this is from her laboratory, and she actually works on identifying deafness genes and collaborates with the regenerative team as well. Now, Stanford, as you may know, has the world's largest regenerative medicine group. It isn't just about hearing. It's about regenerating many other organs, the heart, the brain, the spinal cord. And because there are people with cutting-edge biology in those areas, we're able to work with them and share the very latest in bioscience and technology. We also have terrific clinical programs. We have the Stanford Ear Institute, which takes care of many complicated troubles. And when we have novel therapies, we're going to try them out first at Stanford in our patients. Now, as you know, the federal government has really been cutting back on medical research, which I think is a shame, frankly. Fortunately, we have many donors who help us. But those of you who know people with means, who are able to help invest in what we do, it would be appreciated, because in reality, we know that someday these strategies will work. But whether it's 5 years or 15 or 20 may well depend on how many people we can bring together, how much effort we can put in, and how much we can spend on the kind of cutting-edge technology that we need. So for example, this is the Fluidigm system, which we bought from donor money. It's about $350,000. But what it does, it allows you to study individual cells, one at a time, and look at their genetic makeup and their behavior. And with that system, we were able to take embryos and fate map the individual cells and into how they map to different parts of the otocyst that then become part of the mature hearing organ in a baby. And this is a very important tool for us to be able to manipulate the steps of development. So remember, a lot of this is about turning on the mechanisms that exist in your cells, but doing it during adult life. And doing it in a careful way. Because you know, if you take cells and make them primitive, and switch them on and rev them up so that they keep multiplying, that sounds a lot like cancer, right? So you have to be very careful in this. You have to be able to selectively turn things on, turn them only on for a certain period of time so they don't continue to go forward. And that's why some of these viral vectors, where viruses might spread in the body where you don't want it, hence the need to be able to look in the inner ear, to place something right where you want it to be, and to have it be a molecule which only acts in the location that you intend it to act. This is why we think that's most likely the strategy that will win. So we have been curing, to some degree, mice, and we hope to completely cure a deaf mouse in the coming years, and a deaf human we hope in 10 years, but as I say, I can't make any promises. That is our goal. Now, if we have a few minutes, I want to talk with you, because I know many of you wear hearing devices, and I want to talk a little bit about where hearing aids are going to go and how that's going to interface with the rest of the world. So today's hearing aids, as many of you know, can be very small and very subtle. The hearing aids are moving deeper within, but not necessarily, because these hearing aids block the ear when it's like that, and that's not very comfortable, and it's not very natural acoustically. But some of the hearing aids are moving deeper and deeper in, and an example of that is a very clever hearing aid that's not yet out, but what it is, it's a photovoltaic hearing aid. It is a contact lens for the eardrum that on it has a photocell, and it's powered by a laser beam, and that laser beam has two colors. One, to activate the photocell to give a nanotech motor that vibrates to give it power, and the other for signal. And this is great because it leaves the ear completely open the way Mother Nature intended it, and it allows you to directly drive the hearing bones. So this is fascinating. This is research by a clinical professor in our department called Rod Perkins, and it's coming along. This may be out soon. There are people talking about devices in the middle ear, and frankly, I think this is not that much help so far. We'll see in time. This is the typical hearing aid user in the past. And if you stick a putty-colored thing in your ear, people tend to think that you're 10 years older and that you're, 20 points dumber. But that's changing in a very big way today. You know, it's interesting. If you can see me, if you stick eyeglasses on your face, society says that you're fashionable and you look smart. You stick something on your ear, you're old and you're dumb. Whoever wrote that? That's ridiculous. That stigma about wearing a hearing device has prevented many people from being willing to do it. That's changing and changing rapidly. Today, hearing devices are becoming stylish. Young people are proud to show, look, I've got the latest thing on my ear. Their elegance and beauty. You see celebrities like David Beckham advertising them. They have bling like Paris Hilton. Even Jesus Christ wears a hearing aid. But the point I'm going to make is that wearing an ear device won't be just for those of us who are hearing impaired. In fact, wearing a hearing device, an earpiece, is going to be as common or more common than wearing a wristwatch in the future. Not just in hard of hearing people, but in society at large. And there are reasons for this. Because the earpiece will become a voice-activated cell phone. So I have it in my ear. Cell phone, turn on, phone home. These are some early generation ear-level cell phones. It'll be the interface between you and your computer. You walk into a building, a museum, and this piece, the pictures will talk to you. You go to walk across the street and a bus is coming and it will scream in your ear, look left if you're in London. You'll have all of your books, your audio books. You'll have your music. You don't need an ear pod, an iPod, when you have an ear pod. This is coming. Every year closer to. It will be your GPS. You're driving down the street. How do I get to 1212 Main Street? And your earpiece will tell you. Now, this is remarkable, but it's coming. Someone speaks to you in French. It goes out to a computer in your building and comes back rapidly to your earpiece. Would you like to hear it with a New Orleans twang, or would you rather hear it in a Canadian accent? You can select it if you wish. This is not if. This is coming very rapidly now that we're seeing this. Access to information. Let's say I'm walking up to my friend Mary Jones's house, and I speak to my earpiece. Earpiece, wake up. Mary Jones, 1212 Main Street. What's her husband's name? And in my ear comes Roger. So access to information. And of course, once you have this device on your ear, you can extend the range of hearing. So ever since Galileo gave us the telescope and Leeuwenhoek the microscope to see larger and smaller things, people have wanted to extend vision. We'll be able to extend the auditory range in normal hearing people. We'll be able to digest in a noisy environment and to discern human speech from background noise, and do that in real time through signal-to-noise augmentation. As computers get faster and faster, this becomes more and more possible through signal analysis. And of course, you build in a protection for noise injury. And oh, by the way, once everybody's wearing this earpiece, if you have a hearing loss, you simply turn it up if you need to. So although it may be for just normal people in the population at large, you can use it for hearing. Therefore, instead of only about 20 or 30% of people who could use hearing aids use them, whereas almost everyone who needs visual aids wears either glasses or contacts, we'll see a change where almost everyone who needs help for hearing will proudly wear an ear device. Don't get me started on the cost of hearing aids. They are outrageous. The technology in them is cheap, inexpensive, and that needs to be disrupted. And there's research going on here and elsewhere to bring the cost of hearing aids well down. As a matter of fact, one of the options for a $3 hearing aid is the cell phone. There are now apps that will turn your cell phone into a credible hearing aid if you have mild hearing loss, for virtually no cost at all with an earpiece. Now, once you have on your ear a device with telemetry, with cell phone ability, it can also monitor your oxygen, your glucose, your blood pressure. If you have a little pickup on your chest, your electrocardiogram, think about the Apollo astronauts. With every physiologic parameter, this can be recording your health and your physiology all day, because it's coupled to your body and it's connected through cell phone technology. Well, with that, I want to thank you. This is a bit younger me in Paris. If any of you see this, it's a fun place to get your picture taken. And I'd like to open it up for any questions or comments that you might have.
Thank you again, Dr. Jackler. Very interesting information. Some of the things you talked about made me think like we were watching the Jetsons. It seems like so far in the future, but I know it's right around the corner.
To me, the Jetsons are the past.
Manny wants to know if you need research subjects. He's ready to volunteer.
Yes, if you grow a tail a long snout and whiskers, we're happy to bring you in. But we're not there for humans yet.
Barbara Franklin wants to know if you're doing any research on NF2 hearing loss, example, gene or drug therapy.
Yes. So we are collaborating with treatment of NF2 protocols. We don't headquarter them here. So there's two issues in that. For those of you who don't know what NF2 is, it is a disease in which both hearing nerves develop tumors, and often elsewhere inside the head and along the spinal cord. And I take care of many people and families with this. It's a very different problem than the cochlea, because in this case the wire's been cut, and that's not very common. Now right now we can't replace the hearing nerve, and I don't think that that's nearly as close on the horizon as replacing the hair cells in the ear. So remember, the vast majority of people have hair cell loss, but a few people, like those with NF2, have hearing nerve. There are some electrodes which go against the brain that directly stimulate the brain, and there are some advances in that area. The biggest advances in NF2 have to do with inhibiting the growth of the tumor through blocking blood vessel multiplication within the tumor. No tumor can live unless blood supply grows in the tumor. And there are VEGF inhibitors, several of them in clinical trials, and we participate in that here at Stanford. One is out of NYU, and one is out of Mass Eye and Ear, headed by Bradley Welling. Did I answer your question?
I think so. The next question is about any research that could affect Meniere's disease.
Yes. Yes. Good question. So Meniere's disease is much like glaucoma of the eye, is a fluid pressure regulation problem. The problem in Meniere's disease is that you're constantly making the inner ear fluids, and then you're resorbing it. And what happens, it isn't that you're making too much, it's that it's not absorbing. Imagine there was a hairball in the bottom of the sink, but the faucet kept flowing. And then the inner ear is like a big water balloon, and the water balloon gets tight and swollen. And when it ruptures, boom, it suddenly switches off the ear, and you get horribly vertiginous. There's some research in Meniere's disease, but not enough. I don't think, sadly, that there's that much good research going on with Meniere's disease now. We're learning more and more how well the injectables in the ear work. For example, injecting dexamethasone, just like an orthopedist, when there's inflammation in your shoulder, puts in a steroid. We're doing that in the ear. One area of very relevant research is that right now we use a very crude way of transmitting drugs to the inner ear. And it works, but it's not nearly calibrated as well. So if you think about in the ear, you have two windows, the oval window and the round window. And if you can insert a little catheter there with a tiny micropump to place a calibrated amount of drug right in the inner ear where you need it, that could help in Meniere's disease, to open up, to pull the hair out of the drainage. So there are several groups working on drug delivery to the inner ear, including a number of companies. So it turns out that the ear is becoming very hot amongst pharmaceutical companies. And they're really looking to, they see this as an untapped area. And that's good news for all of us, because it means a lot of brain power and a lot of technology will come to drug delivery in the inner ear, which is really in its infancy today.
Okay, the next question, have any advancements been made for enlarged vestibular aqueducts? And a follow-up question to that, or will guidelines for implantation be changed to include those with EVA?
Yeah, good question. So for those of you who don't know, enlarged vestibular aqueduct is a congenital malformation of the inner ear. Now, just to give you a background, When the inner ear forms, it's a little pouch, and it forms into a spiral to the cochlea. Now that cochlea has two little ducts coming from it, two tubes, one that brings perilymph and one for endolymph. In the case of large aqueduct, the aqueduct that supplies the endolymph is very, very large, and that leads to a variable amount of hearing loss in children. They typically have hearing. It can lead to deafness, or it can be partial hearing loss. So as a birth defect, we don't yet have ways of intervening inside the woman, inside the uterus, unless, of course, it's known to be associated with the genetic syndrome. So the large aqueduct, EVA, is sometimes associated with Pendred's disease, which is a thyroid and ear. And if that genetic defect can be identified, then you may be able to select the fetus, depending on your belief. This is possible now, and even more possible in the future, to not have that deformity in that way. But the problem in a large aqueduct is the same as it is for all the other hair cell losses in time. And that is that the inner ear wears out. So it's very sensitive to bumps on the head and to injuries. And it takes a 90-year lifespan where people gradually lose hearing, and it shortens it. And many kids with large aqueduct begin losing hearing as older children and teens. We're not yet there on fixing it, but the regenerative approach may well help them in time. In terms of implants, kids with large aqueducts successfully have implants quite often. It's not a reason not to have an implant. They do have a little higher risk of spinal fluid leakage, and this gets a little more complicated, something you can talk with your ear surgeon about.
Okay, the next question. Any research for children born without the auditory cortex?
Oh, that's a tough one. So, you know, it's interesting. We used to think the brain was completely plastic. It was all programmed and nothing ever changed. But we learned in recent years that there's much plasticity to the brain. So if a person has a stroke here, the areas around it reassign, and a person who's lost speech may regain it over a few months. And that's not the brain healing, it's the brain reprogramming. Now, where I'm getting to is this. If you're born deaf, and the area for hearing is here in the temporal lobe, what ends up happening, the body doesn't leave that part of the brain fallow. It reprograms it, and in fact vision, which is way back here in the back, tends to take over this area as well as you become visual dominant in your interaction with the world. So I'm not sure what you mean by having no auditory cortex, because in fact the brain is adaptable. So if you're talking about a child who never was stimulated, that is to say, one of the reasons we want to get into a child very young, is before what they call critical period, is so that the brain develops frequency lines for hearing. And the hearing part of the brain integrates with the language part of the brain as well. So children can have their brains reprogrammed by restoring hearing while the brain is still receptive. We used to think that door was closed when a child was 6 or 7. We now learn that's not true. And people who are born totally deaf with no stimulation can still gain some hearing even in young adulthood. But it's not as capable as when you begin very young, so that the brain experiences sound during the developmental period at which the brain is growing very rapidly.
Okay, the next question is, hold on, we've gotten several questions in at the end. I'm not sure we're going to have time for all of them. What do you think of the auditory midbrain implant concept?
Yeah, that's Thomas Lenartz in Hanover and their group. Really don't have much of an opinion. I will tell you, if things go wrong with an implant against your midbrain, it's very dangerous. That's, if you will, the seat of the soul. It's very intolerant, and if you have an injury there or an infection there, it's very serious. So I think it's in development. I think it's worth studying. Give it time. I think it's early.
Are there any supplements or drugs to prevent noise damage?
Yes. If you take a vitamin pill about this big and you shove it in your ears, it will do a very nice job. I'm just kidding, of course. I'm unaware, although the popular press will talk about antioxidants, etc., or vitamins. I'm unaware that there's good science that any of those supplements, or frankly any pills that doctors give you, will prevent noise-induced hearing loss. The most important thing to do is to avoid it, frankly. Now, one thing I recommend to my patients, and I'll show you this on my cell phone, you can get an app, either for free or very inexpensively. Let me hold this up. This is a decibel meter, right? And it will monitor just how loud I'm speaking, which is about 65 decibels now. If you go to your app store for sound pressure or for sound meter, there's a number of them out there. So if you're at a concert and it's getting up to 90 decibels or more, you know you need to be careful. And those of you with hearing loss have fragile ears, because ears that are damaged are more prone to additional loss from noises. So I think you should all carry foam rubber earplugs, and if you're going to be out there, with a chainsaw or lawnmower, over-the-ear muffs, because your hearing is precious, and especially when you have hearing loss, noise can really hurt. 1 + 1 = 4. It can be quite severe for those of us with hearing loss.
Can the inner ear be retrained to recognize higher frequencies?
That's a very interesting question. And the answer to that is very possibly. So there is a training program. So remember what I said about plasticity of the brain. So as you're getting older, you're losing your high tones. So the brain, which used to have levels, I don't know if you can see me pretty well, but low, middle, and high tones. So, if I'm 80 and I haven't heard those high tones for a while, the brain uses those for something else. So then we bring a hearing aid in, and we expect the brain to be receptive. Well, why would it be? So people have suggested that you gradually retrain the brain, and that as you do, you redevelop the brain so that it restores receptivity to high frequencies. So there is research going on about not just taking a hearing aid and sticking it on you, but sequentially retraining the hearing part of the brain to take advantage of neuroplasticity.
You mentioned earlier the research that was being done with cord blood. And is that still continuing, or has the research advanced beyond that?
So the contemporary trend is to use induced pluripotential cells rather than cells from an embryo or cord. There are some private companies who are, for a pretty hefty fee, are freezing cord blood from a child. I don't think that's really about hearing. It's more about, tragically, if a child gets leukemia or something like that, that they have genetically matched cord blood. So I think we've moved away more from primitive cells and moved more into adult cells.
Okay, is the FDA easing the hearing requirements for implant eligibility? Not really sure if that's your area or not.
Yeah, it's not exactly my area, but this really gets down to federal payments for like Medicare or Medicaid or Medicaid programs. And of course the private insurers, the majority of Americans are private rather than governmental insurance. So some of the big issues are about, do you get 1 or do you get 2? And I think the data in children is that 2 for bilateral deafness is better than 1. One of the questions I get often is if we take our child and we put implants in, will that inhibit the ability to later use a stem cell-based therapy to restore hearing? And the answer to that is we hope not, but we don't yet know for sure.
Okay, it looks like we now are out of time, and I want to thank you very much again, Dr. Jackler. This was so interesting. It looks like there are additional questions, but maybe we can save that for another time. And I want to thank also Diana Nichols of ACS for providing CART tonight. And just a reminder that the webinar has been recorded and will be available for replay on our website, hopefully within about a week or so. And we'll post Dr. Jackler's slides with his permission as well. Thank you again, Dr. Jackler, and let's do this again.
Thank you, Nancy, and thank you, Diana. And you know, at some point you might want to have Dr. Stefan Heller on, who can really give a basic scientist perspective on where we are in regeneration. Take care.
That would be great. I'll be in touch with him. Thank you so much again.
Okay.
Good night, everybody.